1952, two brilliant scientists from Harvard and Stanford University were awarded a Nobel Prize for their work and discovery of nuclear magnetic resonance, or NMR. Their discovery eventually led to the development of a machine which has drastically improved modern healthcare and diagnosis. Magnetic resonance imaging, or MRI, uses simple properties of physics to look inside the human body without using invasive or risky procedures. Now, before the invention of the MRI machine in 1977, it was difficult or impossible for doctors to actually diagnose internal problems without actually cutting a patient open on a surgical table. Since MRI has begun, however, it is much easier to do this. And if you or a family member would go to the doctor for an unknown problem, it is much more likely that a doctor will order an MRI for you as opposed to cutting you open on a surgical table. And to prove this point, in a 2007 survey from IMV, a medical industry census, estimated that about 10% of all Americans used an MRI machine in that year. So for the next few minutes, I'd like to show you how the process of MRI works. And I want to begin by showing you the main components of the MRI machine. Now, the components I'll be talking about today are the superconducting magnets and the radio frequency transceiver. Now, as the name magnetic resonance imaging implies, magnets are very important for this. And these superconducting magnets actually can make magnetic fields in the X, Y, and Z directions, so you can create a 3D picture if you need to. And the radio frequency transceiver is able to both transmit and receive radio frequency signals to and from the body. And the importance of this will become more apparent later in my speech. So let's start by discussing these superconducting magnets and what they do. Now, first I need to ask you to recall your basic chemistry classes and how all atoms have a certain spin, which acts like a vector and points in random different directions. Now, the atoms we're talking about with an MRI are hydrogen atoms because they're the most abundant in the body. So, in a normal state, with you sitting here, the spins of all your hydrogen atoms are pointing in random directions, as shown in this first picture. But if you were to go into an MRI machine and a magnetic field were applied, all of the spins of all your hydrogen atoms would be lined up parallel to the magnetic field. Now, as you can see, while they're all parallel to the magnetic field, not all of them are pointing in the same direction. Some have the little purple on top, some have the red on top. And essentially, most of these atoms will cancel out their spins. Those that are pointing up are like a +1, and those that are pointing down are like a -1 to sum to a net sum of 0. And only a few atoms out of every million or so in your body actually don't cancel out. And those are the ones that we're interested in looking at. And for example, those are shown here in blue. And so those are the ones that are going to be most affected by the radio frequency signal, which I'll talk about in this next slide. So the next step in the process is actually applying a radio frequency signal to your body using that transceiver. And what that does is it transmits some energy to those leftover atoms and causes them to be knocked out of alignment with the magnetic field, as you can see here. And then this RF signal is relatively short-lived. And when it turns off, the magnetic field takes over again, and those atoms realign themselves with the magnetic field. In doing so, they emit a certain amount of their own radio frequency energy to the RF transceiver. Now, this energy is specific to the type of tissue that it's coming from. More dense tissue, such as bone or cartilage, it takes a longer time for those atoms to realign themselves with the magnetic field. For less dense tissue, such as fat tissue or internal organs, those atoms can realign themselves with the magnetic field very quickly and thus release more energy. So the final step in the process is when the RF transceiver can receive those emitted signals and synthesize them into an image that we commonly know as an MRI. Now, how this does this is the RF transceiver actually takes those emitted signals from the viewing screen, the viewing field, and uses a Fourier transform, for those of you who are familiar with that. It's basically just a complicated mathematical procedure to turn it into an image like this shown here. Now you can see the clarity of this image with the bone tissue and all the different types of internal organs. And this is a coronal image that cuts through the body this way. And then the next image I'm showing you is a sagittal image, which is cut through the face this way and moves from the ear to midline and then back again. So you can see all of the different types of tissue, the eye socket. Eventually you'll be able to see the nasal cavity as well. And this is one of the advantages of the MRI machine, is that you can see different views from the body without actually moving the patient. Whereas in a CAT scan or an X-ray, if you wanted to get these different views, the coronal or the sagittal or even horizontal, which cuts through the body this way, you would have to physically move the patient. So for the past few minutes, I've gone over the process of how MRI works and explained to you its importance in the advancement of modern medicine. And sometime in your life, you or one of your family members will likely have to use an MRI to diagnose some kind of internal disorder, whether it be just a torn ligament or hopefully not, but a tumor or other more serious disorder. And I hope that my presentation has allowed you to be more appreciative of the simple magnetic and radio frequency principles which allows this to work. Thank you.